one aspect we generally think about such conferences, workshops is that the talks are the most useful. The talks are definitely useful, but the sessions in between are fairly useful. So make good use of them. So I'll now want to introduce the next speaker, Ashish Tendulkar from Google. So all of your Google questions should perhaps go to him. No, I'm just kidding. So Ashish is a very good friend. So we've been discussing machine learning related things since 2019. And he's a very, very enthusiastic machine learning teacher, I would say. And as he says, a learner also. So in fact, he's also very interested in teaching machine learning in regional languages. He has written a couple of very nice blog posts in Marathi. So anyone who understands Marathi should probably just go through that and tell him what you think about it. And he's also done a bunch of teaching for various organizations, including so you might have seen his course, NPTEL course. His NPTEL course he's also an instructor in the IIT Madras BSc program. So I always look forward to his talks. So the way he explains is very useful for me as an instructor. And he does some very cool work at Google Research. He just wanted me to talk about most of the teaching aspect only. So over to you, Ashish.
Thank you. Thank you, Nipun, for kind words and giving this opportunity to talk in this workshop with such an enthusiastic audience. So namaste, everyone. I hope you are all charged up. Huh? Yes. Okay, so I'm going to try this experiment with I need Face ID. Okay, thank you. Should I connect to Zoom? Sorry about that. Is it possible to also connect to internet?
Yeah, so internet.
No, not right now. Later.
Sharing.
There we go. Yeah, there. Okay, we are back. Okay. All right. Okay. So let's first discuss what is machine learning. How many of you have done machine learning course before? Am I audible in the back? All right. So what is machine learning? That's the first question I always like to take. So let's write it down. So you heard formal definition of machine learning in previous talk, right? Do you remember that? Okay. So how many of you code? Everyone? Okay, great. So let's try to introduce machine learning from programmer's perspective. Okay. So I found that programmers understand to machine learning better if I introduce machine learning in this way. So let's take two problems. The first problem is add two numbers. Can you do this? Can you write a program for this? Yes, what is this question? We are here. We know how to do this, correct? All right. So you'll write something like, if you are in Python, you don't even need to add a function for this, but I'm just writing this. So you'll say return a plus b, correct? Simple. Let me write the second question. Now, what we'll do is, I give you an image with a digit written in it. And your job is to take this image as an input and predict what digit is present in this image. How many of you can write a program for this? Don't get confused. Can you write a program for this? No. Right away give up? Yeah, maybe some creative ones will say that I'll write some rules, and based on that, somehow I'll detect this. But then I can always come up with different ways of writing it, right? And your rules will fail, correct? Or I might write it like this. Slightly different, right? But you as human are able to detect these 8s, right? Everyone, I hope, correct? So what is the difference between these two problems? Let's try to understand. Let's try to list out the differences. So what are the differences? Let me make, so one is this addition, and second is digit detection. Thanks. Okay. What are the differences? Yes? Okay, input format is different. But does that really bother you? Because we can also have text input and you can write a program, right, for that. Input format is different. That is a valid thing. But what is even, yes? Okay. Okay. Okay, good. Anyone else? Yes. Sorry, I'll come to you. Okay. Okay. Yes. So I will just write this, right? We know the exact mathematical formula for here, right? We know the exact mathematical formula to achieve this task, correct? Here, we do not have a set formula for this, correct? This is the biggest difference probably, because of which you can write, you can do the first task very easily, whereas second task you struggle, right? So you struggle in terms of writing steps, right? Or writing algorithm, but you struggle when you see these images. You don't struggle, right? Why don't you struggle on these? Because you are used to detect these images, right? You have seen millions of images probably, not millions, if not millions, thousands at least in your lifetime. And you know exactly how 8 is written, or you will use some contextual information and based on that you will say that this is 8, correct? So we know that we can solve the second task. Humans are good at solving the second task. Okay, and one rule of thumb is if humans are good at solving a particular task, we can automate it. But how? How is the question, right? How do we automate this? Let's go to that question. So let's think about the process of detecting a digit. So we said that humans are good at it. Humans are good at detecting digits. Correct? Why? They have seen many examples of such digits. Correct? So now what we want to do is we want to bring in exactly this experience to the computer. Getting it? And that experience is called as training data. This is the first most important concept. What is called as training data? Correct? Repeat after me. No data, no ML. If you don't have any data, you cannot build ML, machine learning or AI for that matter. Getting it? That's very important. So remember this. All right. So now let us see how we can develop a machine learning solution for this problem. Okay. So we need what is called as training data. So how do you get this training data? So you will acquire a lot of images of handwritten digits. Correct? We'll acquire them. And for each one of them, so this is an image. And we will assume that each image has a fixed dimension. So this is, let's say, it's 28 by 28, 28 pixel by 28 pixel. Okay. I have many such examples. And for each of these image, I'll also write what is the label, what digit is present in that image. Getting it? So these are called as examples. And this is called as label. Getting it? These are examples and this is label. Okay, so typically we represent example with letter X. And I'll be using this notation X superscript I. This is ith example. Okay, and Y superscript I is ith label. Getting it? So here, what is X0? X0 is basically this particular thing. Right? So X0 is an image with 8 written in that. There is 28 lines and 28. So basically the 8 is written such that, so there are pixels, right? There are 28 cross 28, that is there are 784 pixels, 28 into 28. And each pixel has a value 1 or 0 if it's a black and white image. Got it? So we have this example represented with 784 numbers. And see, this is where vectors enter into machine learning, right? So we have a vector. Each example is a vector with 784 different components. Getting it? So, and each example, each label, what is Y0 here? Y0 is 8. Getting it? Y0 is 8. And in this case, Y0 is a scalar. And what are we trying to do now? In machine learning, all we try to do is we take this image as an input. And we are going to do some black magic. Okay, we'll go inside it and figure out what that magic is. Right? So this particular box is ML, right? And what this block should do is, this block should ideally give us a function that maps the input to the output. Getting it? And this was the problem, right, for us. Why we were not able to write program for this? Because we were not having concrete function. Right? So what machine learning will do is, machine learning will help us to learn this function. Getting it? So learn function that maps input to the output. Getting it? And this particular process is called as training process. Right? We are at high level right now. We will go into it slowly, how this is done. This is called as training process. Clear? So after training process, we'll have a function that takes input, which are the 784 numbers, and it will give us an output. Correct? And once you have that function, you will be able to write program as you were able to write for adding two numbers. Getting it? So machine learning, we are just going to learn the function or mapping. Clear? So let us quickly write this, right? Let's summarize. This is a traditional program. And this is our ML or AI block. Okay. Now, there are two inputs to this, and there is one output here. So here, what goes in goes data and rules. Correct? Rules and data is what is input, and we get the answer. In machine learning, what goes in? We give data and we give answer and we get rules. You can call it as rules or formula or model. Getting it? Now, people who are not paying enough attention, I'll just mark certain things. So this answer has gone over here. Okay. And this rule has come out. So there is interchange. There is an exchange of positions. Getting it? So this particular process is called training process. We talked about this, right? This is a training process. And after training process, we get rules. And then we can write a program just like this. So this particular process is called as inference. Correct? We don't want to just stop after getting the rule or model. We want to use it, right? We want to use it for making predictions. And that we do by writing a program just like any other program, like addition of two numbers. And that is called as what is called as inference. Getting it? Two steps, training and inference. Clear? Any questions so far? All good, right? Okay. Now let's figure out. Let us find out let us write the building blocks of this process. Yes. Answer is label, right? Answer is what we want. So in case of this example, answer is the labels, the digits that are present in the image. That's the answer. But in some other case, let's say we are solving a problem of predicting whether there will be rain tomorrow or not. Will it rain here or tomorrow or not? So then 1 or 0, right? If it rains, it's 1. If it doesn't rain, it is 0. So the label answer is 1 or 0. It's a label. We have not yet talked about types of machine learning. We will talk about it and then it will be more clear. Any other questions? Right. How do you convert it from brightly colored image? Right. So this is not colored image. This is a black and white image. though it looked colored here, I mean, I have drawn it in a colored fashion. But if you have color image, then there are 3 channels that are maintained: red, blue, and green. So there will be, since you brought this point, we'll have 3 channels here. One channel for red, second for green, third for blue. So it's a tensor. We'll have a tensor. Okay, any other questions? Should we move ahead? All right. Yes. Yeah, so the value over there represent the intensity of the brightness. So in case of black and white image, you will have number between 0 to 255. If it is very dark, number will be close to 255. By the way, there is a very famous data set called as MNIST dataset, MNIST dataset, which is handwritten digit recognition dataset. We'll have it in our practicals in the afternoon. Now let's look at the component of the training process. So let me write this as component of machine learning algorithm, right? Now I'm giving away, this is my favorite topic. I always like to look at any machine learning algorithm with 5 components, right? So take any machine learning algorithm and ask 5 questions and picture will be completely clear to you what is happening. Okay, I'm going to, now this is very, very important. So the first part, what would be the first part? Training data, right? Without data, there cannot be any ML, correct? So training data is the first part. So you should ask question, how does the training data look like for this algorithm, right? What is the input? What is the output? Correct? So what is X? What is the input? And what is the output? Now this output, now remember, Y is output always. Output can be, output can come from a discrete set, right? Something like 0, 1 or red, blue, green, right? It could also be a real number, right? 5, 10.2, 100, -2. Got it? So you should ask, what is your input and what is your output? So whenever you have just 2 of these labels, this is called as binary classification problem. So before that, if your label is from discrete set, this is called as, generally called as classification problems. That's classification. Getting it? And if your label is a real number, it is called as regression problem. Remember this, classification and regression. Now, if you have just 2 of these values, then it's called binary classification problem. If you have more than 2 values, it is called as multi-class classification problem. Getting it? So you should ask this question. What is the type of the problem that you are trying to solve? And what is the data for this? We'll look at examples of these things one by one carefully after some time. And there is one more type which I'll not disclose right now because it will become too complex right now. Let's approach it one by one. Clear about training data? Any questions? All right. Now comes the second part. So second component is, now I told you, right? All that we do with machine learning is learn the mapping or learn the function. Who specifies the function? Humans specify it. But when I studied machine learning, I was never aware of this. I thought this function is also automatically discovered by machines. Right? Everybody naturally thinks that, right? This function is also discovered by machines. So what could be issues in that? There are infinite function classes, right? So which of these functions should be chosen, right? How do you do exploration in this function space? These are all difficult questions, and we do not have computational power for that. We need computational power for that. So in order to have some kind of a compromise, we have a situation where humans specify the function. Got it? So this is where domain expertise come in. Professor Nipun was talking about domain expertise, right? So model is specified by domain expert typically. Even training data, right? In case of training data, where I say X, this X, right? We did not talk much about it, but this X, these are features. What features should be chosen for this problem is also specified by the domain experts, right? And if you want to work in this area of machine learning, be prepared to talk with multiple domain experts and be prepared to be flexible enough and quick enough to understand the other domain, right? Not deeply, but at least to a level where you can have conversations with other folks, right? Otherwise, you'll be talking about machine learning and that guy will be talking about domain. There won't be any, this will be like two parallel tracks, like train track. You will never meet, correct? So you need to have at least 2 times consultation. One is while defining the problem. You need to figure out what features make sense to solve this problem, right? And most often, right, I mean, in my experience, I mean, I'll talk in detail about it tomorrow, but I'll just quickly talk about it. Initial wins in machine learning come by automating the person who is great at that job. You should observe what that person is doing. And that particular thing will give you a bunch of features, right? If that person is not able to specify, by observing them, you can figure out what features are important. And you take them, right? So this comes from domain expertise. Remember, training data, there is a domain experts involved. Model, also there are domain experts involved, right? So what is model? Okay, let's leave aside all these heavy terms like model. Model is nothing but a function, very simple function. So one function that we use quite often in machine learning is called a linear function, right? Linear function. And this is what you learn in probably high school, right? Equation of line. Nobody tells us that this will be useful in machine learning, right? So what is equation of line? Y is equal to mx plus c. I'll write it slightly differently. I'll say that b plus w1 x1, right? x1 is one feature. Now, if we have many such features, we have 784 features, right? I can write this as plus w2 x2 plus w3 x3 all the way up to w784 into x784. Getting it? This is the model. We just specify the functional form of mapping between input and output, right? And by the way, this is the most commonly used function in machine learning. Everywhere, this is the base function, right? You will see this in written in different form, right? So some people will write this. Let's not write this in compactly right now. So what is not known here? Let's understand this. What is known? We know y for training data. We know x1, we know x2, we know all the values up to x784. What is not known? I'm just going to so what is not known? So there are 785 unknowns. Getting it? And these unknowns, there are multiple terms, weights. They're also called as parameters. These are parameters of this model. So this seemingly simple linear model has got 784 parameters in this case, in the case of digit recognition problem that I was discussing about. Clear? Any questions? Feel free to ask questions. No question is a stupid question. Okay, any questions? All right. Clear? We are going slowly. We are learning terms by terms. Weights, parameters, you know now. Now, how do you really fix these weights, and how do you fix these weights? Any ideas? Any ideas? Original ideas? Huh? Permutation combination, right? You randomly set some weights and see what happens. What else? Okay. I see. So you are now talking about some adjustment with respect to something. Okay, that's good. That's good. Anyone else? Anyone else? Yes. Okay, sure. So we set these parameters randomly, for example. And once you set them randomly, you basically have this equation with you, correct? And this equation will give you some value for y. Very easy, right? I mean, you fix these numbers to some random values and you can calculate this equation now. But that may not be, those parameters may not be optimal, but you will get some answer with this, correct? We'll see how to proceed from that. Yes, you had something? Okay, okay. Fair enough. I'll not go with terms right now, so as not to scare others. Yes. You need to, do you get the point that, do you agree with me that we need to find these weights? Unless you find this weight, this function will not be useful, correct? So we need to somehow find these weights. And what do we have with us? We have training data with us. We have some examples where y is given and all these x1 to x784 are given, for example, correct? And with this, we want to do something. So we need something now for that. All of us agree on that, and that particular thing is called as, this is the third component. So what is the first component? Repeat, training data. What is the second component? Model. Good. Third component is called loss. There is a notion of loss. Okay, let's take a simple example. Let's leave aside digit classification for now, and let's take a simple example for this. So imagine you have a value x1 and corresponding output y. And let's say this y is real number, so it's a regression problem. So regression will be taught tomorrow by Professor Nipun again. I'll quickly use this example for motivating loss function. Okay, so we have points like this. I'm just making up some. Now, what is the model here? Simple. There is a single feature, so B and W1 are parameters. Now we want to find out B and W1 such that, so I can set, let's say I set this B to 0, and I set this to, let's say, 0.2. So the slope of the line is very small. So I get some line, this line passing through origin, maybe line like this. Are you happy with this line? Why are you not happy? Not very close. Close to what? Correct. So for example, for this x1, this is the actual value, but the predicted value is somewhere over here. Getting it? For this particular example, predicted value is here and here. These are the predicted values, right? So the difference between actual value and predicted value is quite large. Correct? So how do you define the error here? The error is, so we have to define error per point, correct? So for ith point, we have, let us use this, right? Let me use this for model, H sub W. These are model. Okay, H sub W is a model. Let me not initially use all these things. Let's say we need to have, let's say this is prediction for ith point minus actual for ith point. This is the error. Now, let's say there are some values over here. Then this particular error will be negative, correct? So we don't care about magnitude of the sign of the error, for example. So we can simply square this up. Then everything, each error will be positive. Getting it? So this is error for a single point. Now, we can sum across all endpoints. We get the total error on the training set. This is the error on the training set, correct? And you can normalize this by 1 by 2n by the size of the data set, and this 2 I add for mathematical convenience. Sorry? Why do you? There is something, we will come to that. Hold on to that question. That is one option, but there are some issues with that. We'll talk about it. Yeah. N. N is total number of data points. N, thanks for asking. N is total number of training examples. Get it? Very simple. I have not written any other symbols here right now. Okay, sure. I'll do that. Yeah, it will be possible. I'll do that. Thanks. So n is total number of training example. That was a question before. And so this becomes a loss function, right? So now you can see that if we expand this a bit, right? I can write this as like this. Now this particular part, prediction. This prediction can be written as, how do you write the prediction? B plus W1 xi minus actual whole square. Getting it a bit complicated? Don't worry, we'll do it slowly. So all that I want to establish here is, see this is called as loss, and we'll use this symbol J of W. J is the loss, and this loss depends on the value of W's, right? Or W and B, for example, here, right? So there are two parameters, W and B. So you see that in this equation, right? This part is known, this part is known. What is not known? This is not known and this is not known. So that's why this loss depends on B and W. Getting it? So this is the loss. And this loss now will guide us to decide the right values on B and W such that the overall error is reduced. Are you getting it? What's the point of loss function? The point is, now let's say I draw another line like this. Right? This line has got some W and B's. correct? And with this line also you will get some loss, correct? So eventually you want to get a line which has got the minimum loss, right? So what is the objective here? Objective is to find such that the loss is minimized. Clear? Everyone is with me so far? Any questions? Okay, we are more than halfway done with components. It's third component. And there are different loss functions that we use. Different machine learning algorithms will use different loss functions. Okay, so this particular loss function is called least square loss, and this is a regression loss function. Okay, for classification there is some other loss function. We'll talk about it in detail. Okay, so remember, every machine learning algorithm will have a loss function, and you have to figure out what is that loss function. And that loss function will guide us the how to fit the parameters or what parameters to select. Huh? Okay, good so far? All right. Now, how do you find these W and Bs? Now, all algorithm guys. Now we have come into algorithms. Correct. This is algorithm question. There is no machine learning involved here. This is simple algorithm question. You have to find Ws and Bs such that JW has to be minimized. So what algorithm will you use? Okay, differentiation. How will you use differentiation? Okay, so you're saying that we should be using differentiation. What should we differentiate? We should differentiate loss function with respect to the parameters, correct? That is one way. Okay, is there any other way? Naive way? Is there any naive way to do this? Try all kinds of parameters, right? Try all combinations of Ws and Bs. But it will explode quickly, right? If you have many such parameters, it will explode very quickly. With two parameters, it might be easier. You just have a grid of B and Ws and try different points in the grid. But let's say if we have 10 parameters, this will quickly explode. So it's not a scalable approach, correct? So we need to do something like what he's suggesting. So that's the next part of this. So the fourth component that we have is optimization procedure. So what optimization are we using for this? Okay. So the simplest answer to this is there is an algorithm called as gradient descent. It's a very interesting algorithm. I'll explain this intuitively right now. So let's say we have a loss function. I'm setting B to 0, for example. So now it only depends on W1. And this is my loss. Correct? So that loss function or real loss function, something like this. Right? And remember, each point on this loss function corresponds to the model. Correct? This is one value of W1. This is another value of W1. For each value of W1 and B, we get a model. Are you getting that? If you have forgotten about it, remember. This is for one value of W1 and B. This is another value of W1 and B. This is third value of W1. Correct? So each point over here represent a model. Or a specific instantiation, parameterization of the model. Right now, so gradient descent is simple. Let's say you are at the top of the hill. Let's say you are here, and this is the point where the value of of the loss is minimum. Correct. So you want to ideally reach this point. This is our
target. But let's say you start somewhere over here, you randomly start somewhere over here, and you want to come here. So we use application of derivative, right? We again, nobody tells us that we will be using derivative in machine learning in 12th, right? So calculate the slope of the function here, right? And move in the negative direction of the slope. So you calculate the slope of the function and move in the negative direction of the slope. So you decide to come over here, for example. So imagine you're on the top of the hill and you want to come down to the valley. You look around, you figure out which is the direction of descent, and you will move in that direction, right? You will not fully commit in that direction. You will move a bit and you will stop again. You look around, again figure out what is the direction to go down and move towards that. And you will keep repeating this process. Now this process is called as gradient descent. So it is like that. So this is the first point we started with. We calculate the slope, and this is the slope. So I decide to move in this direction. I come over here. This is my next, this is where I come. Then again, I calculate the slope of the line, move in this direction, come here, right? And step by step, gradually, I'll move somewhere closer to this particular point, right? I stop moving as soon as I see that there is no change in the values of the parameters, or there is no change, or the gradient is close to 0 or something. Getting it? This is gradient descent procedure. So you can use this procedure for any machine learning algorithm. It may not be efficient in all the cases. But if you don't know anything, just remember this algorithm. This will help you in navigating any machine learning training. Okay. And there are, various, there are variations of this algorithm which are more efficient, which are proposed. And we'll see some of them in the next class. Got it? So this is the idea of optimization. So in this case, you are fortunate to have a very nice function which is convex. Convex meaning it has got a single minima. It has got a single minima, right? But we may not be always lucky like this. There could be functions like this. And they're far more harder to optimize, right? And that's where you need some other techniques. So deep learning, for example, has got some such kind of a loss function, which is like egg trait. So this is very hard to optimize. Getting it? Got it? Fourth point is optimization procedure. So after optimization procedure, after running this iteratively, you will find out the values of W's and B's. So you are done, right? Your training process is done. You get values of W's and B's. Then what is the next process? What is the next thing? Now you want to know the fifth step is model evaluation and selection or tuning. You got your parameters. Now you want to know how good is your model for real world case, right? You typically want your model to do well on the future setting, correct? You don't want your model to do well on the training data, correct? But none of us have seen future. So what we do is, let's say this is our entire training data. So we hold out. We do not show this data to the model during training. Okay, so this particular data is called as test data. Got it? And this entire data in black is called training data. So you train on training data and you evaluate your model on the test data. And you will accept those parameters if the model is doing well on the test data. Correct? But how do you know? What do we mean by model is doing well? We need something, right? We need some metrics. And who gives this metric? We define, yes, and domain experts. Again, domain experts. Domain experts give us these metrics. So we typically work with businesses, right? We typically work with business people, right? If you're building a recommendation system, you go and talk with business people, ask them, what do you want this system to do? And then they'll tell you this metric. I want to optimize, let's say, click-through rate. I want to optimize revenue. I want to optimize, the sell. Correct? So you need to have some metrics here, right? So there are some metrics that are standard metrics which are defined for different algorithms. We'll see them. Okay, but the important thing is that we need to have some well-defined metrics. Okay, and then this training test procedure you should think about. Now, why a model which is trained on training data should work well on the test data? You should have that question in mind. Why? We make some critical assumption there. Data is of the same type, yes. So there is a very formal way of saying it. It is data is coming from the same distribution, identical distribution. So we make an assumption which is called as the data is independent and identically distributed. Getting it? So this is called as a very famous IID assumption. So if let's say if I want to find out time to go to, let's say, airport, let's say from IIT Bombay to Mumbai airport, and I give you in training data time from IIT Gandhinagar to Gandhinagar airport, right? You cannot hope to do that prediction task well, because see, training data and test data are different. They are coming from different distribution. The conditions are different. Getting it? Or other example is, as a teacher, right? I tell you that I'm going to test you on machine learning skills. So you'll prepare on machine learning, but in exam, I give you questions in history. Right? You have no hope of doing well because you're not prepared for that. So training data and test data are not coming from the same distribution. Getting it? Getting the point? Now, so there could also be a possibility that this model is doing well because I have this particular data in test data. There could also be a possibility, right? So we also want to nullify this possibility. So for that, what we do is we shuffle training and test data. We test our model on different training and test combinations. Okay, so there is a very, so what we typically do is, let's say this is our entire training data. So we divide this into, let's say, multiple batches. Let's say I divide them into 5 different batches. I partition data into 5 different partitions, each with same number of examples. And then what I will be doing is, I'll be training. So let's call them, right? Let's call these partitions as 1, 2, 3, 4, and 5. In the first training loop, I'll use 1, 2, 3, 4 as training, and I'll test on 5. Got it? This is the first training run. In the second training run, I'll train on 1, 2, 3, 5 and test on 4. Right? So I'll have 5 such training runs. Got it? So this is called as cross-validation. And these partitions are called as folds. And since there are 5 partitions, this is called as 5-fold cross-validation or CV. Getting it? This is more robust way of training machine learning model. See, generally data is scarce, right? So you want to give as much data as possible to the training set so that, model has more information about learning parameters more reliably. That's why we try to give as much data as possible for training. That's the reason. But there could be cases where you have big data, right? If you have millions of rows, we do not train model with a lot of data, right? We might train model with a few 100,000 examples, and you have far more examples in test case. That situation can also happen. But when you have very large amount of data. Okay, any other questions? Yes. It could happen. So all the hope, that's a very good question. So the question is for online audiences, I'll repeat. So what you're basically asking is, our model is working well on a given training and test setup, but what's the guarantee that it will work always well? There is no guarantee. There is a caveat. The caveat is, we guarantee that this model work well as long as the new data is coming from the same distribution as you see in the training. If you find, if your test data or the future data that is coming to model comes from other distribution, you have no hope of learning that well. That is called as distribution shift. We are getting data from some other distribution. It often happens in a real life machine learning system. You train on some data, it works well, but after some days, the data distribution itself changes. So you need to retrain the model in that case. So we'll have those possibilities covered tomorrow when we talk about practical ways of doing machine learning. Got it? Yes. Yeah, so this assembly we do outside. We do this assembly. We'll assemble our training data and we give it to the model. Huh? Other 4 partition. Yeah. So, okay, good question. Good question. The question is, when I train on these partitions, right? Here 1, 2, 3, 4 are training and 5 is test. Second time 1, 2, 3, 5 are training and 4 is test. So the question is this 5, this 4 that we are holding back for test is already seen by the model. No, that is not how training happens. So here we'll run one training loop, okay, and we'll run a separate training loop over here. So this training and this training are not related at all. It's not working. Can you help me with this? Did I press something that did stop working? I think I pressed something. Anyways, I'll hold this for some time. It's 12:04 right now. Okay, got it. So we'll make first. So 1, 2, 3, 4, and 5 as test. There will be one training loop that will be learned. One model is learned that is separate. Now you'll again train it from scratch. That's the second model, and you'll have 5 such models. You will select the one that is giving you the best performance on the test set. Sorry. There could be multiple reasons for that. This one partition on which it is not performing well, it could be that there could be some distribution mismatch or something like that. So we'll have to go and check out that data set. That is one of the debugging strategy. So whenever model is not working well, we go into that, check out what is happening with that data and other things. There could be multiple reasons for that. Now we will train these 5 different models and we'll select the one which has got the best performance on the test set. Getting it? So that's why I wrote model selection here or tuning. Clear these 5 components? So different machine learning algorithm will have these different 5 components. So you should ask these 5 questions and it will be clear to you. So you should prepare a table of these 5 components and after every lecture you should write down these 5 components. Okay, it's a good practice. It's a very modular way of thinking about machine learning. Any question online? No questions. Okay. Okay. Any questions? All good? Chalo. Fine. Anyways, so now what we'll do is we will look at this machine learning visually. Okay, this is another thing I found very useful. Students learn a lot from that. So let me open browser on this machine. So what browser? Let me open Chrome. Okay, so here search for, if you are using laptop, neural network playground. Search for this. Can you see it? Sorry. So this is my inability to work with this platform. Anyways, so see what you see here is there is a machine learning model which is working in browser. There is a tagline. Don't worry, you can't break it, we promise. So feel free to play with it. Got it? So just like what we said, right? There are these 5 components that you will see right on in the browser. There are different type of data sets. There is one data set where these two see where there are these 2 classes which are very well separated, linearly separable. You can draw a line and you can separate them. Got it? The simplest one. Then you have a bit complicated. So there are 2 classes. See, the green one represent one class and orange one represent another class. Okay, this is a classification problem that we are trying to solve. So here it is a bit complicated because it is not separated by line. This is even more complicated XOR style setup. And this is even more complicated. Okay, let's forget about neural network right now. And we just have a very simple setup. So this is the data part. You can set, let's say, 80% data for training and 20% data for test. Right now, keep noise to 0. If you add noise, what will happen is that there will be some kind of corruption that you will see in the data set. So for this data, okay, so for this data, you can see some corruption. You can see that some oranges have crossed over to the blue side and blues have come to orange side, for example, right? So these are complicated problems. So And real life data will be noisy. There will be corruptions of labels and other things. So right now we'll keep it simple. Okay. And this batch size, don't worry about it. So batch size, let's keep it 10. Let's not worry about it. Okay. So this parameter is related to gradient descent. I was talking about gradient descent, right? In order to make gradient descent more optimal, instead of processing the entire data, we calculate gradient on a small set of data. And here we are going to take 10 examples. Okay. Now what we'll do is, see, this is a setup. Huh? This is the model. Okay. The model is very simple, linear model. Linear model is B plus W1 x1 plus W2 x2. There are two features, x1 and x2. Huh? You can see there are two features, x1 and x2. X-axis is x1, y-axis is x2. And we are going to train a model. Now here, don't modify anything else. Now this is the optimization box. This top corner here is optimization piece. So we are specifying learning rate. This learning rate is how much step we should be moving in the direction of the gradient. We said that we will not carry it away with the gradient, right? We'll move a bit. So how much that should be is controlled by what is called as learning rate. Okay. So let's keep it point. Let's actually reduce this. Okay. Learning rate, reduce it to, let's say, 0.001 so that you see the progress. And see, this is a loss. You see loss here. There are some values that are appearing. Correct. So model gets initialized with random weights to begin with. So there are some random weights that are assigned to W1 and W2. So you can actually hover over this blue line and you can see the weight, which is randomly assigned weight. And the thickness of line is proportional to the weight. Thickness of line is proportional to weight. So you will see some random weights assigned on this, right? Now what you do is you press this play button. I'm going to press and you see now what is happening here. See, the model is getting trained. Observe this line, right? This is getting changed. The partition, this partition between two classes is changing. You see that? That is changing very slowly because you have set a very small learning step. So we are going towards the valley, but we are going very, very slowly. Right? And I have purposefully done it so that you can see it changing. Otherwise, it will change very fast. You won't be able to notice. And now see, this is what is interesting. You can see that test loss is 0 and training loss is 0.001. So basically training and test loss, both of them are small and close, which is prerequisite for a good model training. So how do you know whether your model is trained properly? You always look at the test loss and training loss. You will not always be able to visualize model like this because your data will be in multi-dimensional space, right? So what is in our control is we just have visibility into losses, training loss and test loss. Both of them are small right now. And you see this particular curve, right? So this plot is nice and smoothly dipping. So if you see this particular curve dipping smoothly and these two values small enough, then you know that your model is getting trained properly. This is very, very important. Keep this in mind. This is not often explained very explicitly. So just explaining that properly. Okay. How many of you are hungry? Anyways, I'm stopping now. Okay. Stopping this training, not stopping the class. But if you're bored, let me know. We can stop it. So now change it to 0.1 and see the magic, right? So reset it, okay, and run this. So you can see that you reach this zero loss in hardly 90 steps. So you got it. So now I'm taking larger strides. So I'm likely to reach there faster. I'll reach there faster because I'm taking larger strides. Correct? If I take such small steps, it will take me more time to reach there. Correct? But if I take larger strides in 2 strides, I'm here. Exactly that is happening with learning rate. Getting it? Clear? Yes, questions? Yes. Accuracy doesn't decrease, but there are some challenges. So what might happen is, let us go here. So if your learning rate is too large, what might happen is that you risk over jumping this particular minima. You might jump over here. You again jump back here. So you just jump across these two sides without reaching here. If you select very large learning step, you might get greedy and try very large learning step, but you will see this kind of thing. And because of which, the way this particular curve will occur, unfortunately, this is not working. I don't know what's the problem. You basically see a pattern which is like zigzag. This type of pattern. The moment you see this kind of, so that's why it is important to keep track of this curve. This is called as learning curve. If you ever see this kind of zigzag pattern, you know that your learning rate is very large. So what we will do is you will stop the training, reduce the learning rate, and retrain again. Yeah, this is good. So your question is, why are we keeping learning rate constant? Why not variable? So good, you have discovered some algorithm which is already there. So people are doing it. It's called as adaptive learning rate. So there are some variations of these specialized algorithms. People have done that. I did not introduce that right away, but people are doing it. Okay. It's called learning rate schedule. It is used in stochastic gradient descent, where we take one example at a time and calculate gradient. We'll see that later. Okay, is this clear? And if your loss is reducing very slowly, then also you know that this is like happening too slowly. So you increase the learning rate and retrain the model, and it will train faster possibly. Getting it? So in my opinion, right, this is the most important part. See, taking model, training it is very simple. Anybody can do it. But this is real test. This separates good data scientists from the fake ones. Right? Good data scientists will be able to tell by looking at this whether model is getting trained properly. What should we be doing? And if it's model is, now we'll take another case. This is very interesting. Now let's take this case. Right? We have these two features. And let's train the model. This will be even more funny, more interesting, not funny. See what's happening. Learning rate is high, but that is not causing any problems to us because it has still reduced, right? The loss has reduced. It has not zigzagged, so learning rate is okay. But what do you see? There is a plateau that has occurred. What are the values of the losses? Fairly large, right? They are not close to zero. So our model is not converging properly. Right? There is some problem. And now you see that training loss and test loss both are high. Both are high. Now they're trying to tell you some story. What is the story? I do not have enough capacity to learn the pattern in the model, learn the pattern in the data. My model does not have enough capacity to learn the pattern in the data. See what we have done right now is we are trying to learn this circular decision boundary. There is a circular decision boundary. We can see it because we are lucky to have this two-dimensional data. But we are using only features which have no capacity to learn circular decision boundary. With these features, we can only learn lines. Our model is simple. B plus W1 x1 plus W2 x2, which is equation of a plane. So we'll only learn planes with this. Correct? So we don't have enough capacity. Got it? So this is another pulse check. Check whether training and test loss are high. If they're high, then there is a phenomenon which is called as underfitting, which is happening in your model. And what is underfitting? Underfitting means your model simply does not have enough capacity. So what is the remedy? The remedy is to increase the capacity of the model. How? Now I'll tell you. Very simple trick. We'll basically add square term. We'll do x1 square, we add x2 squared, and we also add x1, x2, for example. Second order polynomial, right? This is polynomial transformation. I'm applying polynomial transformations on the features. P x1 squared, x2 squared, x1, x2. So earlier I had 2 features, now I have 5 features. So naturally the capacity of model has gone up because now I can now fit different type of functions. more complex functions. So now you see this. Now we will again train and see the magic. And many students actually feel that this is magical. This is still not magical. Let me reduce learning rate a bit. Okay, I'm not sure. Let me remove this. Let me remove this. Oh, is it correct data set? Yes, it's correct data set. Fine. Oh, what's happening here? Still there is some problem. Yeah, let us see, Let me train slowly. Let me train faster. Right, this is not working right now. Resetting everything. This is not working. I'm adding these two features, for example. See the magic? You can see it, right? We have suddenly learned circular decision boundary. Why are we learning it? Because now we had x1 squared and x2 squared added. Let me add this back also. I'm not sure why this failed today. This is crazy. This should not have failed. There is some issue with this today. Forget about this. Clear? Now you see the training and test losses are small. And there is no zigzag pattern here. Model is trained properly. Clear? Got it? So we learned a bunch of things with this visual exercise. Any questions? Now we have 8 minutes left. I should probably open the floor for questions. Do you have any questions on this? Which rectangular? This one, right? This one? Actually, our learning rate is too high, so that's why we are not able to see the progression. Now you can see it. Because of which it suddenly comes to 0. And initialization is probably good. Because of which it is initialized close to the optima. So it quickly reaches to optimum and done. Isn't it magical? Many people feel that this is magical. But understand the concept. There is a method, there is a theory. And I want you to understand this properly. Okay? All right, so play with this if you get some more time. So, this particular thing will be very useful when you learn deep learning, deep network, neural network models, right? Add actually layers like this, hidden layers. So I will not talk much about this because somebody will talk about it later. But you can use this when you learn neural networks. Okay? And you will actually see magic. I'll just show you one magic and I'll go away. Now what I'm doing is, I'm not adding these two guys. I'm not adding x1 squared and x2 squared. But I am adding, instead of that, I'm adding some complex machinery here, a network here, right? And I'll show you that this learns it. This is too slow. Let us see, this should work. It's strange. Something is broken actually in this. Something broken. These loss values do not make much sense to me, actually. This works. Stuck into some bad initialization. So later when you learn neural network, right? I mean, try this, okay? It's actually very interesting. with neural network, right? With deep learning, you'll be able to learn these complex representations, polynomial representations, by adding this machinery in between. But that's not the point of today's class. Right now, we added this, and we showed that it works well. Got it? Good enough. Any questions? Yes. It need not be convex always in nature. It depends on, okay, the question is why the curve is convex in fourth step, in optimization step, right? This one, right? This one was complex. I was showing you the case of least square error. I was showing you this curve corresponds to the least square error. The least square error was here. This one, this is the least square error. And if you actually use this function and actually plot this particular curve, it will look like this. So this is a convex, but this need not be convex always. I was telling you about this another case of deep learning models. It need not be convex always. It depends on how the loss function is selected. So if your loss functions are convex, your machine learning algorithm development is less painful, right? So you should always try to, even if your objective, even if your loss function is some weird function, right, which is non-convex, always try to come up with a convex approximation to it and work with it if you can. Because it becomes far more easier to develop algorithms with that. Yes, other question? Yes. Right. This is not a line. Now, okay, that's good. So the question is, in earlier case, we were looking at line fitting. Here, we are not fitting line. Our objective is to learn the boundary between two classes. What is the loss? Yeah, it can be curve. See, you can see a curve here, correct? This is a curve. And we are able to learn curve here because we have given that kind of representation. X squared term, x1 squared, x2 squared. Right? Remember equation of circle, correct? So you can fit any curve. So if you include even higher order polynomial terms, x1 cube, x3 cube, x2 cube, you will have cubic functions. You will have fourth order functions. But of course, there is a price to pay, right? There are no free lunches. As you increase as you increase the order of polynomial, number of features will also go up. And there's a price to be paid. When you have more parameters to fit, you need far more data to fit them appropriately. Otherwise, your model will overfit. Overfitting means model will have so much of capacity that it will remember everything. So remember, I mean, if I give you a question bank of 10 questions and say that come tomorrow for machine learning class, and I just give you one of those 10 questions, you will do extremely well. This is called overfitting. Because you have understood, you have mugged up everything and come to the class. If I give you slightly different question, you may not be able to answer that because your model is not trained properly. It is just trained on those 10 questions. Right? So that is called as overfitting. You have remembered your training data well because you have excess capacity. You have so much capacity in the model that you have remembered your training data. But if I give you anything outside training data, you just fail. So there is a possibility of overfitting with very large polynomials. So we need to guard against that. We'll have some techniques that we'll learn next time. Yes.
Two very good questions from the online audience. Number one is that how do I know? So what are the criteria to assess how good a model is? Is the loss function the only metric?
Okay.
That's question number one.
Okay. So loss function is not the only metric. The loss function is, I would say, a surrogate metric that is used, which is mathematically convenient for us to fit the function, right? But actual metrics are the ones that are defined by domain experts, or there are some other metrics like precision, recall in case of classification. We have not talked about them. I'm just throwing some terms right now, but there are some other metrics that also we evaluate. That is good enough for right now.
Just to add that we will have lectures on model validation, model evaluation later in the course. And the second question, also a very nice question. Does every machine learning algorithm use gradient descent?
Not really. Gradient descent can be used, but it may not be the optimum choice for every machine learning algorithm. So every machine learning algorithm uses some optimization procedure, need not be a gradient descent. Right? Yes. Anyone else? Yes. That depends on the optimization algorithm. Optimization, okay, the question is, how do I know if the solution that I obtained is correct? That depends on, again, your skill of applying that optimization algorithm, whether you have trained it, whether you have given it enough time to optimize, explore possibilities, and also depends on your loss function. If your loss function is convex, and if you have set up the parameters of optimization function properly, and given it enough time, it is guaranteed to converge. But if you have non-convex function, then it really depends on where you initialized, how many times you initialized it, and yeah, there are many other factors. So it totally depends on how well you have optimized it. That's another art in training machine learning algorithms, especially deep network models. Okay, any other questions? Good question. So the question is, here we are able to see it because the data is visual, right? 2D. So that's what I was telling you, right? I mean, our best friends are these. Remember, always do not look at this. You should always look at only these two things. Not really. Sorry about that. Okay. See these two things. These are your friends. Always. Look at these values: test value, training loss, right? Training loss, test loss. If your model does not have enough capacity, your model will underfit. And when your model underfits, your training and test losses will be high. When that happens, you know that your model is has an issue of underfitting. Then you go ahead and add polynomial features. First add two second order polynomial feature. Again, train the model. Okay, if you are not patient enough, add a very large polynomial features. Okay, then you will have another problem. Your model will overfit, and there are ways to guard against that, which is called as regularization. We'll see that there is a guard against that. So throw in large polynomial features, apply good enough regularization, and again train the model and look at these numbers. Always keep looking at these numbers and this particular learning curve. Yes. Huh? Which features? So the question is, can we study these features? So typically, we started with machine learning. So I did not tell you few other things that we do before machine learning. We'll cover that tomorrow's thing. There is something called as data pre-processing and data exploration, which is a step before machine learning. Whenever we get data, we do not go and build models. Sometimes we do it just to see what is the baseline. But typically, we analyze the data, we visualize the data, we study what are the features, whether those features are correlated with the output. We do a lot of those kind of studies before even applying models. We'll talk about that in tomorrow's class. Any other questions? I know we are a bit over time. Yes. This is just for demonstration, but I find this very useful tool for students to visually understand what is happening in machine learning. And this actually helps you to understand all components and a lot of these concepts, which otherwise is very difficult. So treat this as a tool where you want to just check your understanding. If you figure out something, just go and quickly try it. Right? Any other questions? Yes. Sorry? X and Y, these inputs. These are just some inputs. There is no meaning to this. This data is in this format. So the question was, what does features represent here, x1 and x2? There is no representation. This is some synthetically generated data set. Graph meaning this particular graph, right? The reason is, okay, so the question is, why do we want this particular learning curve to look like this? See, what does it represent? So x-axis is basically iterations, iteration, and y-axis is loss. So if your model is training properly, what should happen? Your loss should decrease with every iteration, right? Because you are learning something. When you are learning something, your loss should go down. If your loss is going down in after every step, then you should get a smoothly decreasing function. That's why we want this kind of graph. Sometimes if you are jumping over the other side, then you will see zigzag type of pattern, and then that's a problem for us. Or if this graph is just too flat, then you know that your learning rate is too small. You are making very slow progress. Increase the learning rate. Yes. Any other questions? Okay, I don't want to stand between you and lunch. Let's call this off. Thank you very much for patiently listening and asking questions. We'll have one more fun session in the afternoon. Okay, that will be after lunch, so I hope you will not sleep in that.